A reaction related to esterification is lactone formation, where we end up forming a lactone, which is a cyclic ester. So let me show you more about that one. This also gives us a good time to bring up the effective ring size. And what we notice about ring size is that the 5, 6, and 7 rings tend to be the most favorable ones. And the reason for that is because if we look at 3 and 4 membered rings, you can see that we're going to have unfavorable bond angles. In the instance of the cyclopropyl type ring, we're going to have a 60-degree in this one and 90-degree, and you know that these bonds, the single ones, want to have a sp3 hybridization, which is 109.5 degrees. So these ones are thermodynamically less likely because they're less stable due to their ring strain. For the ones that are 8-membered rings and above, we're talking about kinetically less likely compounds. Now the reason for that is because if you've got an 8-membered ring, or you want to try and form an 8-membered ring, here's what you're trying to do. You've got 1, 2, 3, 4, 5, 6, 7, 8. You've got all of this stuff here, and the chances of this getting around to attack this C are very less likely because you've got all of the different ways that this OH can orient itself. It can be sticking down here, it can be sticking over here, and getting it to actually get within striking distance of this C double bond O is going to be difficult, and that's going to be the way it is for 8-membered rings and higher. Alright, so what that leads to is just the usual formation of 5, 6, and 7-membered rings because they have the right bond angles, and they also have the ability to get the O within striking distance of the C double bond O in the cyclization step. Alright, so let's take a look at the mechanism here and also take a look at the pattern. I've modified this pattern slightly based on the esterification one, and what I've done is I've put the OH as part of the same molecule because that's the way it is in the lactone reactions. The OH is not part of a separate alcohol coming in as part of the same molecule that has the ends up going to having the C double bond C double bond OH in that same molecule. Alright, so what's going to happen here is that we've got the XH group, and again we can see the same pattern being obeyed. The X is going to come in and end up replacing the Y, and we're going to end up with YH. So in this instance what it is the X group is pretty much everything that's connected to C double bond O on this side. And then, whoops, that's minus the hydrogen of course. And then we're going to have the X group connected to the C double bond O, and then this will be the Y group, and this will be YH, and there's your X group there. So it's still pretty much the same as the esterification, it's just done in a cyclic environment. Let's take a look at the mechanism for this. So the first step is the C double bond O attacking the H plus. And the nucleophile comes in, and the nucleophile is actually the OH on the other end of the chain, and that's our cyclization step. And that's going to give us a 5-membered ring. Now, as I've said in the esterification reaction, what we notice in the proton transfer step is that the proton will always be transferred to the group that's leaving. The group that's leaving will always be the Y group, that is the group that was originally attached to the C double bond O in the molecule, and that's going to be this OH here. So I'm going to go ahead and do that. Transfer the proton to the Y group. And then we can reform the C double bond O and get rid of the leaving group, which forms our lactone and H2O, H+.